Module 6, Lecture B, K-means clustering. By the end of this lecture, you will be able to explain clustering as finding structure in unlabeled mechanical engineering data, implement K-means assignment and centroid update steps from scratch, evaluate cluster usefulness through plots, centroid interpretation, and engineering context. Unsupervised pattern discovery. Unlabeled data patterns. In mechanical engineering, data is often collected without labels that identify known conditions or outcomes. Sensors may record signals such as vibration, speed, temperature, surface roughness, or tool temperature, but not whether the system is operating normally or under a specific fault or process state. Clustering is useful for this kind of unlabeled data because it looks for natural patterns in the measurements, helping engineers discover structure and gain insight without training on known answers. Unlabeled data can be explored by finding observations with similar measured features. In clustering, algorithms such as K-means group nearby data points around central points called centroids, without knowing what the groups mean. For example, machines with similar vibration patterns under similar loads may be placed together, while engineers interpret the resulting clusters using their knowledge of the system. Clustering helps reveal useful patterns in unlabeled engineering data, where systems may operate in modes that were never documented. It can separate conditions such as low demand and high load, distinguish material processing histories, or identify driving behavior patterns from sensor data. These patterns become most valuable when engineers interpret them using domain knowledge. Python code unlabeled data patterns. Clustering helps uncover hidden operating patterns in engineering data, even when the measurements are unlabeled. In this example, synthetic pump sensor data is used to show how similarity in the data can reveal useful structure. We import NumPy to work efficiently with arrays and numerical calculations. We also import Matplotlib's plotting tools to create visualizations and examine patterns in the data. To make random results repeatable, we create a NumPy random number generator and set its seed to 7. This produces the same sequence of random values each time the code runs, which helps with teaching, debugging, and comparing results consistently. We create a NumPy array of 3 coordinate pairs, where each pair represents a hidden operating regime in the simulation. Each pair gives a pressure value and a vibration value, serving as the center for generating synthetic pump data under different operating conditions. We create synthetic pump data by generating pressure and vibration samples around predefined operating centers. For each center, random values are drawn from normal distributions using a pressure standard deviation of 3 and a vibration standard deviation of 0.18. With 18 samples per center, the final dataset contains 54 measurements that reflect realistic variation across operating regimes. This check confirms that the synthetic pump sensor dataset has 54 rows and 2 columns. Each row should contain 1 pressure and 1 vibration measurement. If the shape is different, it signals a problem in the data preparation process. 3 initial centroids are chosen by copying selected data points, specifically the 2nd, 24th, and 43rd entries. These starting positions are then used in K-means clustering, where the centroids are iteratively adjusted to better represent the data. The K-means algorithm runs for 6 iterations, repeatedly refining the clusters. In each iteration, it measures the Euclidean distance from every data point to each centroid, assigns each point to the nearest centroid, and then updates each centroid to the average position of the points in its cluster. This process gradually moves the centroids toward better representatives of their assigned clusters. We count how many data points belong to each cluster using NumPy's nCount function. Setting a minimum length ensures all 3 clusters are included, even if one has no assigned points. This provides a quick summary of how the data is distributed across the clusters. The output first reports the total number of pump records to show the dataset size, then gives the number of observations in each cluster. It also explains that the cluster centroids represent pressure in psi and vibration in inches per second. Because the clusters are not labeled with specific conditions, their meaning must be interpreted using engineering judgment. We begin by creating a new plotting area with Matplotlib. The figure is set to 7 by 5 inches, giving us space to display patterns found in the data. This creates a scatter plot, where each point shows a measurement, with discharge pressure on the x-axis and vibration velocity on the y-axis. The points are colored by their k-means cluster labels, using the Viridis color map to make the groups easier to distinguish. This plotting step marks each cluster centroid with a red X, making the centers easy to distinguish from the data points. These centroids show the typical patterns found by the k-means algorithm. The plot labels discharge pressure in pounds per square inch on the x-axis and vibration velocity in inches per second on the y-axis. Its title explains that k-means clustering is being used to find patterns without condition labels. A subtle grid improves readability, and the displayed plot supports visual interpretation of the clustering results. This script shows how k-means clustering can find patterns in unlabeled pump sensor data. It creates synthetic pressure and vibration readings around 3 operating conditions, then repeatedly adjusts cluster centers based on the nearest data points. The output reports the size and final center of each cluster, and a scatter plot highlights the grouped readings and centroids. The main idea is that clustering can reveal hidden structure in data, but understanding what the clusters mean still requires domain expertise. Hidden data groups. Mechanical engineering data often comes from sensors or experiments without labels showing what is normal or problematic. Clustering helps reveal natural groups in measurements such as vibration, temperature, speed, and load. By comparing data across several dimensions, engineers can uncover hidden patterns and gain useful insight from unlabeled datasets. Hidden groups in data may reveal patterns that were not defined in advance. For example, clustering pump measurements such as flow rate and pressure can identify shared operating behaviors, including efficient performance or unusual vibration. These discovered groups can guide maintenance decisions and help engineers understand what influences system behavior. Hidden data groups found through clustering should be treated as starting points for investigation, not final answers. Clustering reveals numerical similarity, but domain knowledge is needed to explain what the groups actually mean. In engineering data, clusters may reflect real system behavior, different failure modes, usage patterns, or outside influences such as test conditions or weather. The value comes from combining computational results with engineering judgment to turn raw patterns into useful insight. Python code, hidden data groups. Hidden groups can exist even when data has no labels. In mechanical measurements, similar behaviors may naturally cluster together, and this example introduces the basic idea using simple k-means steps. We begin by importing NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for visualizing data. These libraries provide the basic foundation for the analysis and visualization tasks in the script. To make random results repeatable, create a random number generator with NumPy and set its seed to 7. This produces the same sequence each time the code runs, which helps with debugging and checking results. We create 3 unlabeled groups of pump behavior data to simulate different operating conditions for clustering. Each group has 12 samples with 2 features: flow rate and vibration. The normal group has moderate flow and low vibration. The hot group has higher flow and higher vibration, and the vibrating group has lower flow with the strongest vibration. The observations from the normal, hot, and vibrating pump groups are combined into one dataset using NumPy's vertical stack function. This creates a single unlabeled collection of all pump observations. A shape check confirms that the dataset contains 36 observations, each with 2 features. We initialize k-means by choosing 3 starting centroids from the dataset, using the 1st, 15th, and 29th observations. These starting points guide the clustering process. So we also check that the centroid data has 3 rows for the 3 groups and 2 columns for the 2 features. The algorithm repeats 6 times to improve the cluster centroids. In each pass, it measures the Euclidean distance from every observation to each centroid, assigns each observation to its nearest centroid, and then recalculates each centroid as the mean of the observations in its group. This gradually moves the centroids toward the centers of their clusters. The code counts how many observations fall into each hidden group using NumPy's bin count function. It ensures the count includes all 3 groups being analyzed, even if one has no observations. This gives a quick view of how the observations are distributed across the clusters. The output summarizes the clustering results for the pump data. It first reports the total number of pump records, then shows how many observations fall into each hidden group. It also lists each group's centroid, giving the average flow rate in gallons per minute and vibration level in millimeters per second. Together, these values provide a concise engineering summary of the discovered pump behavior groups. The plot visualizes k-means clustering results for pump data. Each observation is shown as a colored point based on its assigned group, while the group's centroids are highlighted with large red X markers. The axes show flow rate in gallons per minute and vibration level in millimeters per second, with a title and light grid to make the hidden pump behavior groups easier to interpret. This script shows how k-means clustering can find hidden patterns in unlabeled pump data. It creates measurements for normal, hot, and vibrating pump behavior, then groups the data by repeatedly assigning points to the nearest centroid and updating those centroids. After several iterations, it reports the size and center of each discovered group using flow rate and vibration level. A scatter plot then shows the clustered points and their centroids, illustrating how k-means reveals structure in mechanical measurements. Engineering data patterns. In mechanical engineering, clustering helps find meaningful patterns in measurement data, even when labels are unavailable. For example, vibration data from a rotating machine can be grouped by similar features such as amplitude and speed. These groups may reveal different operating conditions, like smooth or imbalanced operation. This makes clustering useful when failure data is limited or missing. Engineering data becomes more useful when connected to the physical systems that produce it. Clustering measurements can reveal meaningful operating states, such as stable machining, tool wear, driving behavior, road conditions, or heat exchanger modes. In this way, clustering helps engineers turn raw measurements into a clearer understanding of how systems behave under different conditions. Clustering helps mechanical engineers explore complex data before making decisions by revealing natural groups, such as different normal machine states or similar prototype test results. It does not judge whether a group is good or bad. engineers must interpret the patterns using domain knowledge like load ranges or material properties. In short, clustering organizes the data, while engineering insight gives the groups meaning. Python code: engineering data patterns. This example shows how clustering can uncover hidden operating patterns in engineering data. It uses simple synthetic sensor data and implements k-means without relying on machine learning libraries. We begin by importing two key libraries: NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, they provide the basic foundation for the data analysis and visualization tasks in the script. To make random data consistent across runs, use NumPy's random number generator with a fixed seed. Setting the seed to 7 produces the same random sequence each time, which helps with debugging and checking results. 3 operating regimes are defined as pairs of vibration amplitude and temperature values. These pairs serve as the centers of synthetic data clusters, representing different engineering conditions. Data generated around these centers can then be used for clustering to identify patterns. Synthetic vibration and temperature data is generated around predefined operating centers using normal distributions. Vibration values use a standard deviation of 0.45, while temperature values use a standard deviation of 3.0. Each center produces 18 data points, and the results are combined into one dataset that reflects variation across the operating regimes. This check confirms that the dataset has 54 rows and 2 columns. It verifies that the generated data has the intended size and structure before clustering begins. If the shape is different, an error is raised to signal a problem with data generation. K-means begins by choosing initial centroids from the dataset. In this case, the observations at positions 0, 20, and 40 are copied as the starting centroids. These starting points guide the algorithm as it repeatedly adjusts them to find natural clusters in the data. The k-means process runs for 6 iterations to refine the clusters. In each round, it measures the Euclidean distance from every data point to each centroid, assigns each point to the nearest centroid, and then updates each centroid to the average position of the points in its cluster. Repeating these assignment and update steps moves the centroids closer to the centers of their groups. The code counts how many observations fall into each cluster using NumPy's bin count function. It tallies the cluster labels and ensures there is an entry for each of the 3 clusters, even if one has no observations. The result is a simple count for each discovered group. The code reports the results of clustering unlabeled vibration and temperature data by similarity. It shows how many observations fall into each cluster, giving a quick sense of group size. It also explains that the cluster centroids represent typical vibration values in inches per second and temperature values in degrees Celsius, helping interpret the main characteristics of each group. The code loops through each cluster centroid and prints a short summary for that cluster. It reports the typical vibration and temperature values, rounded for readability, so the clustering results are easier to interpret. We begin by creating a new plotting canvas with Matplotlib and setting its size to 7 by 4.5 inches. This gives the visualization enough space to be clear and readable, which is especially useful when presenting clustering results. This creates a scatter plot of vibration and temperature measurements, with each point representing one data pair. The points are colored by their cluster labels, making the groups found by clustering easier to distinguish. A gradient color map and a clear point size help make the clusters visible. The scatter plot marks each cluster centroid using its vibration and temperature coordinates. These centroid points are shown in red with a large X marker, so they stand out from the other data. This makes it easier to see the central tendency of each cluster in the engineering measurements. The plot uses clear axis labels to give the data engineering context. The horizontal axis shows vibration amplitude in inches per second, while the vertical axis shows bearing temperature in degrees Celsius. These labels make the measurements in units easy to understand. The plot is finalized by adding a clear title that explains its purpose, using k-means clustering to find patterns in unlabeled engineering data. A subtle grid improves readability, and displaying the plot lets us interpret the clusters, data points, and centroids visually. This script shows a simple k-means clustering example using synthetic sensor data for vibration and temperature. It creates data for 3 operating regimes, then repeatedly assigns points to the nearest centroid and updates each centroid from its assigned points. After several iterations, the data is separated into 3 clusters, revealing typical sensor patterns for each group. The output reports each cluster size and centroid, and a plot visually summarizes the grouped data and cluster centers. K-means steps. Initialize centroids. K-means clustering begins by choosing initial centroids, which serve as starting guesses for the clusters. Each data point is assigned to the nearest centroid, and the centroids move to better match their assigned points. Because these starting positions influence both speed and the final grouping, choosing them well is important. In k-means, centroids can be initialized by randomly choosing a fixed number of data points as the starting cluster centers. The remaining points are then assigned to the nearest starting center. This approach is simple and requires no prior knowledge of the data structure, but results can vary when groups overlap or outliers are present. When implementing k-means, centroid initialization is a crucial design choice because poor starting points can lead to weak or misleading clusters. To improve results, choose the number of clusters in advance, use valid data points as centroids, and reduce sensitivity to randomness by running the algorithm multiple times or using an initialization method that spreads centroids across the dataset. Python code. Initialize centroids. This demonstration shows how random centroid initialization works using a small set of mechanical measurement data. The focus is on a short visual explanation of how starting centroids are chosen at random before clustering begins. The script begins by importing NumPy for efficient numerical work with arrays and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for data analysis and plotting tasks. To make synthetic vibration data repeatable, the random number generator is given a fixed seed of 7. This makes the same random values appear each time the code runs, supporting consistent results and easier debugging. The speed and vibration measurements are stored in a 2-dimensional NumPy array, where each row contains one shaft speed value and its matching vibration amplitude. This structure keeps the data organized and ready for later analysis, such as clustering. The code adds more synthetic measurement points, each pairing shaft speed in revolutions per minute with vibration amplitude in millimeters per second. These data points simulate mechanical readings and will be used to initialize centroids for clustering similar measurements. We choose 3 as the number of groups for the k-means clustering algorithm to find in the data. This choice guides how the algorithm separates similar data points, so selecting an appropriate number of clusters is important. Here, 3 clusters are used based on the data or prior knowledge about it. The code first checks whether there are enough data points for the requested number of clusters. Each cluster needs a unique starting point, so the dataset must have at least as many points as clusters. If not, the code raises an input error to stop the clustering process before it fails. To initialize clustering, we randomly choose a set of unique data rows equal to the desired number of clusters. These selected rows become the initial centroids, so each starting center is a real data point. We copy them to set up the cluster centers while leaving the original data unchanged. We first show which dataset rows were randomly chosen as the initial centroids, so it is clear which data points start the clustering process. These centroids are real measurements from the dataset, not arbitrary values. They are then displayed rounded to 2 decimal places to give a clear view of their starting positions in the feature space. This plot sets up the starting point for k-means clustering by showing measurement data and the initial centroids together. Each measurement is plotted by shaft speed on the horizontal axis and vibration amplitude on the vertical axis, while the centroids are shown as larger X markers. Axis labels, a title, a legend, and a light grid make it clear how the data points and starting centroids relate before clustering begins. This script shows how to choose starting centroids for k-means clustering using synthetic shaft speed and vibration amplitude data. After creating a repeatable dataset, it verifies that enough points are available and randomly selects 3 existing measurements as the initial centroids. It then reports the selected points and displays them on a scatter plot, with the centroids marked clearly to show the algorithm's starting positions. Centroid update. After assigning each data point to its nearest centroid, the algorithm updates each centroid to the average position of the points in its cluster. The centroid is not an original data point, but a summary of the cluster's typical profile across all features. This refinement is important because the starting centroids are only rough guesses, and repeated updates help them better match the structure of the data. In k-means, updating centroids is a repeated recalibration step. After data points such as pump test results are assigned to clusters, the algorithm recalculates the center of each group. These new centers can change which points are closest to each cluster, so assignment and updating repeat until the centroids or cluster memberships stop changing. When updating k-means centroids, each centroid is moved to the center of the points assigned to its cluster. Feature scales must be handled carefully, so larger units do not dominate the result unless the data has been scaled first. If a cluster has no points, you must either keep its old centroid or choose a new data point. This update makes centroids better summaries of the groups in the data. Python code. Centroid update. This example shows how centroid updates summarize assigned engineering measurements using a small set of pump operating data. The centroids are recalculated from scratch with NumPy to represent the current groups of measurements. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting module to create visualizations, helping us display data and interpret the results of our analysis. We create 2 NumPy arrays to store measurements from 6 small pumps, one for flow rate in gallons per minute and one for vibration in millimeters per second. Both arrays use floating point values, so the data is ready for accurate numerical analysis. The flow and vibration measurements are combined into one 2-dimensional data matrix using NumPy's column stacking function. This places the 2 features side by side for each of the 6 pumps. An assertion then checks that the matrix has 6 rows and 2 columns, confirming the data is structured as expected. We initialize the clustering process with 2 centroids, each described by flow and vibration values. The first starts at 49 flow and 2 vibration, and the second at 83 flow and 5.7 vibration. A shape check confirms that there are exactly 2 centroids and 2 features for each one. To assign pumps to clusters, we compare each pump's measurements with each centroid and calculate the Euclidean distance between them. This distance is found by combining the squared feature differences and taking the square root. Each pump is then labeled with the cluster of the nearest centroid. To update the centroids, first make a copy so the original values are not overwritten too early. Then, for each cluster, gather the data points assigned to it. If the cluster has any assigned points, replace its centroid with the average position of those points across all features. The output summarizes the pump clustering results by showing each pump's assigned cluster and the original and updated centroids in a readable, rounded format. The centroids are then interpreted to explain the main patterns. One cluster reflects typical low-vibration pump behavior, while the other reflects high-vibration behavior. This gives engineers a quick view of how the pumps are operating. The plot visualizes a k-means centroid update for pump data. It shows flow rate on the horizontal axis and vibration on the vertical axis, with pump points colored by their assigned cluster. The original centroids are marked as red crosses, while the updated centroids are shown as black stars, making it easy to compare their movement. Labels, a title, and a light grid provide context and improve readability. This script shows one update step in k-means clustering using pump flow rates and vibration levels. It starts with 2 centroids, assigns each pump to the nearest one using Euclidean distance, then recalculates each centroid as the average of its assigned points. The updated centroids represent typical low and high vibration pump behavior, and the visualization shows how the centroids move after reassignment. Centroid update. After each data point is assigned to its nearest centroid, the centroid is updated to better represent its cluster. It moves to the average position of all assigned points across the features, acting as a summary of the group, rather than a real data point. Repeating this adjustment helps refine the initial rough centroids, so they match the structure of the data more closely. In k-means, the centroid update recalculates the central profile of each cluster after data points are assigned. For example, machines grouped by vibration and temperature may form clusters with different typical sensor patterns. When the centroids shift, some machines may fit better in a different cluster, so the algorithm repeats assignment and updating until the clusters are refined. To update centroids in k-means, recompute each cluster's center by averaging the feature values of the points assigned to it. Each new centroid should keep the same measurements as the data, such as pressure, flow rate, and temperature. If a cluster has no assigned points, either leave its centroid unchanged or reinitialize it. Repeating this update helps the clusters move toward a stable solution. Python code, centroid update. Demonstrate how centroids are updated from scratch using a small set of mechanical sensor measurements. Keep the explanation concise, visual, and focused on the essential idea. Each centroid shifts toward the average of the measurements assigned to it. We import NumPy to handle numerical work with arrays and matrices, which supports the computations needed in the code. We also import Matplotlib's plotting tools to visualize the data points and show how the centroids move during clustering. Store the vibration and temperature measurements in a two-dimensional NumPy array, where each row is one measurement point. The first column holds vibration amplitude, and the second holds operating temperature. This structure makes the data easy to analyze with NumPy array operations. We start the clustering process by choosing two initial centroids as rough cluster centers. One is set at 0.2 inches per second of vibration and 41 degrees Celsius, while the other is set at 0.75 inches per second and 76 degrees Celsius. These starting points are then refined iteratively based on the data. First, we check that each data point and each centroid have the same number of features. This ensures they can be compared feature by feature during clustering. If their dimensions do not match, the data structure is inconsistent, and later calculations may fail. To assign points to centroids, we compare each point with every centroid and calculate their Euclidean distances. These distances form a matrix, with one row per point and one column per centroid. For each point, we choose the centroid with the smallest distance, producing an assignment that shows which centroid each point is closest to. To update centroids in k-means clustering, we first keep a copy of the current centroid so the originals are not overwritten too early. For each cluster, we gather the data points assigned to it, and if the cluster has any points, compute their average across each feature. That average becomes the cluster's new centroid, moving it toward the center of its assigned points. The output compares the old and new centroids, rounded for easier reading, and shows which points are assigned to each centroid. This makes it clear how the update step changes the clusters. In this iteration, each centroid moves toward the average position of the points assigned to it. The plot uses different colors to show cluster assignments, making it easy to see which data points belong together. It also marks the original centroids with black crosses and the updated centroids with red stars. This comparison shows how the centroids move toward the centers of their assigned clusters after the update. The plot is prepared by labeling vibration amplitude on the x-axis and operating temperature on the y-axis, so the data is easy to interpret. Its title explains that it shows centroid updates after one assignment step. A lightly transparent grid is added for readability, and the plot is displayed to help visualize how centroids and data point assignments have changed. This script shows one basic centroid update using vibration and temperature sensor data. It starts with two rough centroids, assigns each data point to the nearest one, and then moves each centroid to the average of its assigned points. The printed values and plot show how the centroids shift toward the center of their clusters. This is a single iteration of a k-means style clustering process. Cluster review. Centroid interpretation. In k-means clustering, a centroid represents the average profile of a cluster, so it should be interpreted as a typical pattern rather than an exact data point. In mechanical engineering, this can help connect groups of sensor or operating data to meaningful states such as high load, higher temperature, or moderate vibration. The main goal is to compare each centroid with the overall dataset and relate its notable features to known conditions such as normal operation or possible faults. When interpreting k-means centroids, always consider the scale and meaning of the features. If the data was standardized, centroids describe relative positions rather than real physical values, so they must be translated back into practical terms. A pattern such as high temperature and vibration only becomes meaningful when judged against actual levels and system context. Good interpretation combines statistical results with domain knowledge, to explain each cluster in terms of mechanical behavior and operational decisions. Centroids are useful summaries for judging whether clusters are meaningful. If centroids are very similar, the clustering may be too detailed or uninformative, while a distinct but unrealistic centroid may point to problems with the data or settings. Visual tools such as scatter plots can support interpretation, but centroids should guide hypotheses and decisions, not serve as definitive proof. Python code, centroid interpretation. Interpret cluster centroids by relating them to the engineering features they represent. Compare each cluster center with the overall feature averages to understand what makes each group distinct, and present the results with one clear plot and brief printed summaries. We begin by importing 3 core Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps organize and analyze tabular data. And Matplotlib's plotting tools let us create visualizations to interpret results. We generate reproducible mechanical operating data by using NumPy's random generator with a fixed seed of 7. Each of the 3 simulated operating state clusters is set to contain 18 data points. This defines a small set of centroid-like operating states for mechanical data. Each state is described by vibration, speed, temperature, and load, ranging from low load conditions to higher stress conditions with greater vibration, temperature, or load. These centroids act as reference points for clustering and interpreting different machine operating conditions. The code defines feature names for key engineering measurements: vibration amplitude, rotational speed, temperature, and load. Including their units makes the data easier to interpret and supports meaningful analysis later. To create compact clusters for each state, a noise scale is defined to control how much each feature can vary around its true centroid. An empty collection is then prepared to store the generated points for each cluster, representing realistic variation in mechanical operating data. For each true center and cluster size, we generate a group of normally distributed data points around that center. The noise scale controls how spread out the points are, while the cluster size controls how many points are created. These groups form simulated clusters that represent mechanical operating states with realistic variability. The code uses NumPy's vertical stack function to combine the generated data blocks into one dataset. The result is a 2-dimensional array with observations as rows and features as columns. An assertion checks that the final dataset has 54 rows and 4 columns, confirming the blocks were combined correctly. To prepare data for k-means clustering, each feature is standardized using its mean and standard deviation. This shifts the feature values so they are centered around 0 and scaled to have a standard deviation of 1. Standardization is important because it puts all features on a comparable scale, so no feature dominates the distance calculations simply because its values are larger. To begin k-means clustering, we choose 3 observations from the standardized data as the initial centroids, giving the algorithm starting points from different areas of the dataset. We also create an empty label array for all data points, which will be updated as each point is assigned to its nearest centroid during the iterations. The k-means process runs for 8 iterations to refine 3 clusters. In each round, it measures the squared Euclidean distance from every standardized data point to each centroid, assigns each point to the nearest centroid, and then updates each centroid to the mean of the points in its cluster. Repeating these steps gradually moves the centroids toward the centers of their assigned data points. The standardized centroids are converted back to their original units by reversing the standardization process, using the original standard deviations and means. This makes the centroid values interpretable on the same scales as the engineering features. The converted centroids are then organized in a pandas data frame with feature names as columns, making them easier to review and analyze. The code adds an interpretation column to the centroid data after converting the centroids back to physical units. This column gives each cluster a clear operational label, such as normal efficient operation, heavy warm operation, or a high-risk thermal vibration state. These labels make the clusters easier to understand without needing to inspect the underlying numbers. The output first notes that the cluster centroids have been converted back to their original engineering units. It then summarizes each cluster by printing its number, interpretation, and key centroid values for vibration, temperature, and load. The values are rounded for readability, making it easy to compare clusters and understand the operating state each one represents. This visualization shows the original data points using vibration amplitude and bearing temperature, with colors indicating their assigned clusters. The cluster centroids are overlaid as large red X marks, making the typical operating states easy to identify. Clear axis labels, a descriptive title, and a light grid help make the cluster structure and centroid positions easier to interpret. This script creates synthetic mechanical operating data, groups it with k-means clustering, and explains the resulting centroids in engineering terms. After standardizing the data, it repeatedly assigns observations to the nearest centroid and updates the cluster centers. The final centroids are converted back to vibration, temperature, and load values, then labeled as operating conditions such as normal efficient operation or a high-risk thermal vibration state. A scatter plot highlights the clusters and their centroids to summarize the main operating patterns. Centroid interpretation. Centroid interpretation means explaining a cluster's center in practical engineering terms. In k-means clustering, a centroid represents the average behavior of the observations in that cluster, such as a typical vibration pattern or a common temperature and pressure condition. Although it is not an actual data point, it summarizes the cluster and helps turn mathematical results into useful engineering descriptions, such as high load and temperature or low vibration with stable speed. When interpreting cluster centroids, always consider the scale, units, and meaning of each feature. If the data is not properly prepared, features with larger numeric ranges can make a centroid look misleading. In machinery data, values such as shaft speed, vibration, and temperature must be compared with known operating ranges and thresholds. This helps engineers decide whether a cluster represents normal operation or a possible problem. Interpreting centroids helps show whether clustering results are useful by connecting each cluster to practical engineering meaning and possible actions. In a pump fleet, this might reveal patterns such as efficient operation, high energy use with low output, or mechanical instability. Centroids should still be checked with plots and domain knowledge because they can hide variation or reflect noise. Reliable interpretation requires both technical analysis and engineering judgment. Python code, centroid interpretation. This example shows how to interpret k-means centroids using the engineering meaning of each feature. It uses a small set of pump operating data and implements k-means directly without machine learning libraries. The script imports 3 key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze tabular data. And Matplotlib's plotting tools create graphs and charts. Together, these imports prepare the script for data manipulation, analysis, and visualization.
A random seed is set, so any random operations give the same results each time, supporting reproducibility.
The data then defines fixed pump measurements for flow rate, power use, and vibration level. Together, these engineering features describe pump operation and prepare the dataset for later analysis.
The flow, power, and vibration measurements are combined into one data matrix using NumPy's column stacking function. Each row represents one pump observation, and each column represents one feature. A shape check confirms the matrix has 9 observations and 3 features, so the data is ready for further analysis. To standardize the data, first find the average and standard deviation of each feature across all observations. Then, subtract each feature's average from its values and divide by its standard deviation. This gives each feature a mean of 0 and a standard deviation of 1, helping all features contribute fairly to clustering distance calculations. The clustering process begins by choosing 3 starting centroids from the scaled data, using the first, 4th, and 7th observations to represent different parts of the dataset. A label array is then initialized with zeros, ready to store the cluster assignment for each data point based on its nearest centroid. The algorithm repeats 6 times to improve the centroids. In each pass, it measures the Euclidean distance from every data point to each centroid, assigns each point to its nearest centroid, and then updates each non-empty cluster centroid using the mean of its assigned points. Repeating this process makes the centroids better match the structure of the data. The standardized cluster centroids are converted back into the original engineering units by applying the original standard deviations and means. This makes the results interpretable as flow, power, and vibration values. The converted centroids are then organized in a data table, and a cluster size column is added by counting how many data points belong to each cluster. The process interprets each pump cluster by reviewing its centroid values in engineering units. High vibration indicates mechanically unstable behavior, while high power combined with high flow indicates high output, high power operation. Clusters that do not meet those conditions are treated as efficient low-load operation. The final output summarizes each cluster by its pump count and the meaning of its operating behavior. This plot visualizes pump operating clusters by showing each pump observation as a scatter point, with flow on the x-axis and power on the y-axis. Point colors indicate cluster membership, while larger black cross markers show the centroids that summarize typical operating regimes. Labels, a title, a legend, and a light grid are added to make the chart easier to interpret before displaying it. This script uses k-means clustering to group pump operating data based on flow, power, and vibration. After standardizing the measurements, it repeatedly assigns points to the nearest centroid and updates the centroids, then converts the final results back to original units. The 3 clusters represent high vibration mechanical instability, high output, high power operation, and efficient low load operation. The script summarizes these operating regimes and visualizes them with a scatter plot. Centroid interpretation. In k-means clustering, interpreting a centroid means giving engineering meaning to the numerical center of a cluster. The centroid is not usually a real observation, but it represents the average profile of the points in that group. This helps describe clusters as practical operating states, such as low load or high temperature conditions, rather than just points that are close together in feature space. In this way, centroids connect mathematical clustering results to useful engineering insight. Centroids should be interpreted in the context of the system, not just as raw numbers.
Patterns such as high vibration with high temperature may suggest a warning state, while low fuel use with stable torque may indicate efficient operation. The meaning of each value depends on engineering expectations and domain knowledge, so clustering results must be interpreted alongside the specific system being analyzed. Centroid interpretation checks whether clusters form a clear, meaningful story about the data. Distinct centroids that match known engineering conditions can support decisions, such as identifying normal operation, tool wear, or different driving patterns. If centroids are too similar or lack practical meaning, reconsider the number of clusters or the features used. Always combine centroid review with plots and system knowledge to confirm the patterns are useful. Python code, centroid interpretation. Use the engineering meaning of each feature to interpret cluster centroids. Synthetic pump data makes the clustering easier to understand, while plots help connect the numerical centers to practical meaning. The script begins by importing 3 key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze tabular data, and Matplotlib's plotting tools create visualizations. Together, these imports prepare the script for data manipulation, analysis, and visualization. We initialize NumPy's random number generator with a seed of 7, so it produces the same random sequence each time the program runs. This makes the results reproducible and consistent across runs. Three engineering operating prototypes are defined as centroids for clustering. Each prototype is described by flow rate, pressure, and efficiency, one at 35, 18, and 72, another at 62, 31, and 84, and a third at 88, 46, and 68. These centroids provide reference points for grouping similar data points in the dataset. We generate 18 data points around each prototype centroid. Noise is added in each dimension using standard deviations of 4, 2.5, and 3, creating realistic variation around the centroids. This produces a more natural data set for clustering analysis. We create an unlabeled set of pump operating measurements by generating noisy samples around each true center. For every center, random points are drawn from a normal distribution using that center as the mean, a chosen noise level as the spread, and a fixed number of points. Each group of generated observations is stored together, forming blocks of data around the underlying prototypes. The code uses NumPy's vertical stack function to combine the generated data blocks into one dataset. The result is a 2-dimensional array where each row is an observation. It then checks that the final dataset has 54 rows and 3 columns, confirming the data was combined correctly. To standardize the dataset, we find the mean and standard deviation for each feature, then adjust each value by subtracting the mean and dividing by the standard deviation. This gives every feature a mean of 0 and a standard deviation of 1. Standardization is important in clustering because it helps each feature contribute fairly to distance calculations. We set the clustering process to find 3 groups in the data. To start the k-means algorithm, we choose 3 observations from the scaled dataset as initial centroids, the 1st, 21st, and 41st. These starting points are selected to be spread across the data, helping the algorithm converge effectively. The k-means process repeats for 8 iterations. In each pass, it measures how far each data point is from each centroid, assigns each point to the nearest centroid, and then updates each centroid to the average position of the points in its cluster. This gradually moves the centroids toward the centers of their assigned groups. The centroids are converted back to their original engineering units by reversing the earlier scaling, using the standard deviations and means.
This makes the values meaningful for interpretation. The converted centroids are then organized in a pandas data frame with columns for flow in gallons per minute, pressure in psi, and efficiency in percent, making the results easier to analyze and present.
The centroid data is sorted by flow rate to make the clusters easier to interpret. This places the clusters in a logical order for pump analysis, where flow is often a key factor. The index is then reset so the data stays clean and sequential for later use. The output explains how to interpret pump operation centroids by summarizing each cluster's key values. For every cluster, it reports the flow rate, pressure, and efficiency, giving a concise view of the operating profile represented by that centroid. The code summarizes the clusters by interpreting their centroid patterns in engineering terms. It labels them as low load, efficient mid-load, and high flow lower efficiency regions, turning the numerical clustering results into practical engineering insight. This visualization plots pump flow rate against efficiency, with each data point colored by its cluster label to show operating groups. The cluster centroids are overlaid as large red X markers, making them easy to identify as representative pump operating profiles. Axis labels, a clear title, and a light grid provide context and make the plot easier to interpret. This script demonstrates k-means clustering on synthetic pump data to identify meaningful operating regions. It creates noisy measurements around 3 prototype conditions, standardizes the data, and refines 3 clusters through several iterations. The final centroids are converted back to flow rate, pressure, and efficiency, then interpreted as low load, efficient mid-load, and high flow lower efficiency regions. A scatter plot with highlighted centroids helps show how the clusters relate to practical pump behavior. In this lecture, you learned to explain clustering as finding structure in unlabeled mechanical engineering data, implement k-means assignment and centroid update steps from scratch. Pause briefly. Evaluate cluster usefulness through plots, centroid interpretation, and engineering context. In the next module, Module 7, we will go over none.
Thank you for your attention. See you all in the next lecture.